You may know that the definition of DTFT. At this moment, we will study a little bit practical way. What is the DTFT, discrete time Fourier transform? Here shows a waveform. The LED waveform is plotted over time. This one is a time axis. This LED one can be decomposed into several different spectral components. One is the blue one. That's the fundamental frequency. And the green one is 3 times faster compared to the fundamental. And purple is 50 times. So this original waveform can be decomposed into 3 different spectral components. By taking the DTFT, we can find out the spectral contents of this original waveform. It shows here that this one is time axis, but this one is frequency axis. DTFT converting the time domain LED component into a spectral component. Here shows that the blue one is this frequency component, and the green one and purple one. So by taking DTFT, this time domain waveform can be plotted over frequency domain like this way. So to a little bit practical understanding, let's do some example by use of Excel. Okay. To make it sample this LED one, we can assign the number of sample. At this moment, the number of sample is about number of sample 16, and gating time, this time is 1 second. Then sampling period is P2 over P1 second. So this is sampling frequency. I just sampled 16 of this one. So this time is just they sliced by 16. So the sampling period is given here. Then sampling frequency is 1 over Ts. Okay, this one is a sampling frequency. And omega s is 2 pi times, okay, omega s equals 2 pi divided by Ts. Okay, this one is radian per second. Okay, we set it up in this way, and let's give an index. We have 16 samples, so we're starting from 0 and the plus 1, and the 16 then will be 1 more. So this is a number of 16. So we have 16 samples. Time, then index times Ts will give Ts make a constant. So this is actual time. This is the time axis. Okay, I think this is better. And the original signal is a sum of 3 different spectral contents. So the XST is a sum of 3 different frequency components. The frequency is 1 Hz. I just assume that this one is 1 Hz. That means this is 1 second. And the green one is a 3 Hz, and the purple one is a 50 Hz. So I don't like to generating these signal. So X1T is the first fundamental frequency component, and X3T is a third harmonic T. Okay. Okay. The next one is X50T. It's a fifth harmonic. So to calculate that one, I need to calculate the sine wave. I would like to plot this one. Sine wave 2 pi times frequency is this one, and time is this one. So I generated this one, but I hear that this frequency should be pinning at this 7th, okay, seventh position, and time always at the B column. So I make it constant. Then I can stretch out in this way. Then this one is frequencies F7. Okay, this one. And this is frequency and this one is time. So I can stretch out that one into time domain. So I generated sine and third harmonic and fifth harmonic, and this is the sum of this component. Okay, then this is it. So sample is not that much larger, so that is not that much smooth, but we can see the effect. Okay, I'd like to insert. Okay, what about this one? Okay, data, choosing. First one is this fundamental frequency component. So index is changing from here, and the signal is this one. Okay, here shows the one of the frequency component of this one. The blue one are plotted over here. The next is a green one, also plotted in the similar way. Add data, and this one is a third harmony, and x-axis will changing over here, and the third harmonic spectral contents is this one. So 24. Okay, but this one should be scaled down. Okay, I have to use chart type should be linear. The sampling is not that faster, so it shows a little bit distorted, but I would like the dividing factor is 1/3, and this one is 1/5. Okay, then this will scale down in this way. So the blue one is this one, and the third harmony is this one. So I'd like to change this color with green one. Color as a green one. Okay, that is this green one, and the last is fifth harmonic, and choose x-axis and y-axis. Okay, that's this one. So here shows 3 spectral contents of the signal. Okay, these 3 components are plotted over here. And what about the original waveform? The original waveform is the sum of them. Okay, x, I use the index of this one, and y value is sum of them. Okay, this one corresponds to, I'd like to change it to LED. Oh man. Okay. Let's change into LED color. Okay, this LED one corresponding to here, this LED one. So here shows the original spectrum of that one, but we would like to study the DTFT. By definition, DTFT can be obtained by use of definition like this. Sum over n xn start say omega and n. This is the DTFT definition. So I would like to find out that one. In fact, this one is the matrix calculation. To find out that one, I choose the omega value first. I would like to calculate frequency at the 0, 1, 2, 3, 4, and 5. We can do more, but I would like to calculate only those frequency component only. So to figure out those frequency, I would like to write down the frequency component over here. Frequency 0 and 1 Hertz and 2 Hertz, 3, 4, and 5. So I would like to find out that these frequency component from this one. What frequency component are included here? So I would like to find out that one. So to find out this one, you know what, this summation is just a matrix operation, and time index, this is frequency, and this is time index. Time index are changing from 0 to 15. So I can with about 4. Okay, then okay, this is the matrix that I would like to calculate. I would like to calculate this one in this way, that at here the omega is a matrix, so x equal to j omega will have some 0, 1, 2, 3, 4, and 5. I'd like to calculate that part. So it means that x j omega 0 and x j omega 1, like that. I would like to find out those frequency component of that. That can be described by some matrix and the data. This matrix will be the given at a given specific frequency, but you know what, this one is all those one a sine basis one. So I can write down, we have to calculate the cosine and the sine, but at this moment the cosine component is 0, obvious. Okay, obviously the cosine component is 0. So this can be find out some time index. I have xn like this one, x1, x0, x1, x2, x15. Okay, this is the data that I have. That's this data. Okay, that is this one. But what we need some basis function. Basis function can be understand that a00, a01, okay, a015. Okay, this is first law, and the second law is a10, a11, a115. Okay, and this one will be repeated. Okay, and the last one is a fifth 0, a fifth 1, last one is a fifth 15. Okay, could you read this matrix? I think it should be around here. Okay, this matrix is called basis. How can I create that basis? So that is here topic. So these spectral contents should be given here. So I would like to find out that one over here. That's the x is j omega. So I would like to calculate over here. That's the unknown that I have to find. So after that, I create this one. So x is given here. So this can be expressed a x in this way. X is a basis function. Okay, just a basis function x, like that. Then by calculating this matrix operation, we can find out the spectral contents of that one. What kind of spectral contents do we need? That is given from this matrix. Okay. From here, I would like to create the basis function of A here. So the vertical row corresponding to spectral contents, the horizontal column corresponding to this time. Okay, this time index. So basis function of matrix A, as I shown here, this one can be given as a sine function. Because this one is a sine base, not the cosine base, 2 pi times spectral contents is this one, and time index is this one, but the time is sampled by the sampling period. Okay, that should be constant. Then this gives the basis function. Okay, let's a little bit consider a little bit detail. From here, 2 pi times frequency. Frequency axis, this column should be fixed. Okay, row will be changed, and this I15, you know that this is time index. Time should be given as the 8th row from here. So this should be make it constant. So h is constant, 8 is constant, and then I sweep that into these directions and in these directions. Then I created matrix A. This one is matrix A. So I would like to make a name. This one is A basis. So I named it AB. Okay, this is AB. And this is the XS. So I named it XS. Okay, then I need to calculate the spectrum. Spectrum is just a matrix multiplication between A basis versus XS. Okay, A basis times XS will give the spectral contents of that one. Then I got it. This one shows that the spectral contents, the frequency, fundamental frequency, and the third frequency, and fifth one, only these frequency components exist here. Okay, if I need more spectral contents, I can add that one, like this one, 7, then 8, like that. Then I can do the same multiplication from here, A basis and XS. Okay, I think fifth. Okay, I understand. The AS is defined onto here. I did give another name. So AX. Okay, AX is this name. So at this moment, I have to take AX, not AB. So the matrix size should be this large. Then I can get it. So it has only this frequency component, and this one is non-zero, and this one is non-zero. Well, how much this one is scaled? So 8, 2.6, and 1.6. Other things are almost 0. So we know that this one is a unit, but this one is 1/3 of that, and this one is the fifth one is 1/5 of that. So you can understand this spectral contents can be find in this way. 8 is fundamental, and divide by 3 will third harmonic. And fifth harmonic, 8 divided by fifth, will give this value. So this is the spectral contents of this original waveform. So if we have only the red one, that's this one. Then we have a basis function, basis matrix. Then by product of the matrix multiplication, we can find out the spectral contents of that one. I just show you how to find out the spectral contents by use of this Excel function. The same can be done by use of MATLAB. I would like to show you how to make it. So okay. First, I need to define the number of sample. N is 6. Clear all and clear screen and clear variable, and I define the number of sample is 16, and gating time is 1 second. Then sampling period is 1 Tg over n. This is sampling period, and the sample frequency is 1 over Ts, and omega s is 2 times pi times Fs, or 1 of Ts. Okay, this is pretty fine. And first, I would like to generate time series. Time series is this one. Okay, so to find out, I need n index and time series should be found. So n is given as a 0 to the n minus 1. So that's this part, 0 to the n 15. So that's this part. And what about Ts? Time series is n times t sample time. That gives this value. And next one, I would like to generate signal. Signal can be generated here. That the first one is sine 2 times pi times the fundamental frequency component is this one, and third harmonic I just scaled down 1/3 and sine times 2 pi times at this frequency is 3 and time series, and fifth harmony is a scale down 1 over 5 and sine 2 times pi times 5 Hertz times Ts. So this create this LED block. So this LED data access is generated like this way. So fundamental, third and fifth harmonic are added. The scale factor is 1/3 and 1/5. Okay, and next I would like to create the basis function. Okay, basis matrix. At this moment I would like to check up the frequency over 0 to 8 as I have done over here. 0, 1, 2, 3, 4, 5, 6, 7, and okay, this is 7. Okay, anyway, I can using this one. This spectral content will be evaluated, and then the normalized frequency is 2 times 5 times frequency. This is omega, as we have done in previous class. The omega is this large omega. Okay, this omega 2 pi f, and I have to multiply Ts, then it becomes normalized frequency. So I need to make it normalized by multiplying this one. So this one is a real frequency, angular frequency, but I make it normalized by multiplying Ts as we have done here. Okay, this is normalized frequency, and I would like to create the basis matrix. So blank basis matrix are created here. So index are changing from 1 to the length of omega. Okay, and AX are generated by appending each row. each law will be given exponential 1j times omega times n. So this will give a basis matrix are generated. That's this part, creating this one. At here we only consider the sine terms, but at here I consider the exponential j omega something. So this one contained cosine plus j sine omega. Okay. Okay, I created the basis matrix. Then I can take DTFT. DTFT is possible now. DTFT is just like this way. Xs are found AX times XS. As I talked to you that this one means the DTFT operation by taking the matrix. And finally, I would like to check that it is correctly working. First, figure 1 will plot the time domain signal TS and XS. And next figure, I would like to plot the spectral contents. To plot that one, I would like to start in frequency. That's this one, and ABS of XS. Spectral magnitude will be plotted. I would like to run this one. Okay, here is line 23, column 3, line 23, 26, 26. Okay, the column should be taken like this way, because this basically is not a row matrix, it's a column vector. So I make it row vector. Then, okay, it's working. Then I can see here, this one is a time domain plot, and this one is a spectral contents. So you can compare the matrix, the Excel example. This red one corresponding this time domain plot. These spectral contents are plotted over this axis. So the 1 Hertz is 8. Okay, that's this one. 1 Hertz is 8, and other terms are 0. The 3 Hertz is 2.6. That's this point, and the 5 Hertz is 1.6. Okay, this point. Only these three spectral contents are show up here. Next, consider that the window size effect. It means that basically omega is continuous variable, so I can extend this value like okay, here. Remember this figure first. Remember this figure. So I would like to add more spectral contents here. It means that I have only 0 to the 8 as an integer number, but I would like to increase this one by use of linear space. 0 to the 8, number of points is 101. Then I sample a little small frequency resolution. Okay, I increase this frequency resolution at here. Then what's going to happen? So I'd like to run this one, show here. So time domain is the same, but the spectral domain is a little bit different. It has more samples around here. We have only the 1 Hertz signal, and this one's 3 Hertz and 5 Hertz, but there is some different components seems like exist, but it is a false value. Okay, this one. So why this is happen? That is because of the window effect. So to reduce that one, I can increase the number of samples about 30 to 64, and sampling time is this way. Then sampling time is increased, and the number of gating time is extended. At this moment is 1 period. I give gating times 2, then that is the 2 period will be given. So let me run this one. Then I plotted the 2 period of that one, the gating time, and the number of sample is increased up to 64, and then the spectral content is changed in this way. So 64, then what will be changed? So that's this one. But at here still there is some false spectrals exist here, around here. It means that even though we increase the the number of sample and gating time. Something changed, but still some residual errors exist here. So what if I increasing this one up to 4? Then I extended 4 seconds. At this moment, I take the spectrum by use of 1 second data, but now it's 2 seconds. What about 4 second cases? So this is 4 second cases. I have included the 4 period of that one, and then it is a little closer that the residual error is reduced a little bit, but still remains. Okay, so you need to understand what's the relationship between the gating time and number of point. If we increase the number of point 128, then what will be changed? So it is a little bit smoother, but it doesn't that much change in the spectral contents. Spectral contents affected by the gating time. Okay, if you increase this one like 8, then the spectral contents will be changed. Let's see. Okay, see here. So I extended the gating time. At this moment 8 seconds. It is a little bit sharper. So I can figure out that there is a 1 Hz and 3 Hz and 5 Hz. So it's important to increase in the frequency resolution. I said that this one is frequency resolution are controlled by the gating time. Okay, if you're increasing gating time, it means that I need to more longer period of time I gated data, and that will affecting the spectral contents. Think about it, why this gating time are affecting resolution in the spectral domain. So by use of DTFT, we can converting time domain signal into the spectrum and in reverse way. That operation just a matrix operation like this way. Okay.